Well, I've only got about 10 minutes, so what I'm going to try and do is just give you a really brief introduction to the use of thermal mass for low energy heating and cooling, both in dwellings and commercial buildings. So I haven't really got much time to do it, to give it, much coverage and go into detail. But what I will say is that we have publications on our stand. We have one called Thermal Mass Explained. It will take you through the basics. And we have another one on passive and active cooling in commercial buildings, which is very much in line with what we've just heard about the white collar factory. And there's lots of different ways of exposing soffits and lots of case studies in there. So anyway, a brief overview. And I'm going to start with dwellings and show you how you can optimize the design of your dwelling to get some passive heating during the heating season, which is something that's not often talked about. And it's technically called passive solar design. You may have come across it. And as Elaine said earlier, it's really important to get the bones right of your building, and I think that also includes orientation. It's really great if you can orientate buildings on a north-south axis or within about 30 degrees of south. And there's a number of reasons for doing that, but essentially it boils down to good daylighting, it avoids glare, it makes shading on the south elevation really easy, just using deep overhangs for the roof, for the first floor level, or maybe balconies or brise-soleils. Any kind of overhang really will keep out the high-angle summer sun to prevent overheating. But it also allows, importantly, some useful passive solar gains during the heating season. And just to show you what I'm talking about, this is a Google model which allows you to look at daylighting and shading to see how effective different options are. So this is a south-facing room, lots of south-facing windows. We've got a simple brise-soleil to keep the summer sun out. But this is actually a day in February, so we're in the heating season, and it's 8 o'clock in the morning, and low-angle winter sun is already shining into the building, not obstructed in any way by the overhang, which is what you want. So shining from the east onto the sidewall, and as we go through the day, you can see the sun tracks round onto the floor, and if you've got a bit of thermal mass in the building fabric, it's going to soak up some of those solar gains and hold on to them. And then later in the day, as the temperature starts to drop, some of that heat is re-radiated back into the space, and it just reduces the load on your heating system by around 11% or thereabouts. It'll vary on the design. Doesn't sound like much, but you know, this is free passive heating. It's going to happen for the life of the building. It doesn't require any maintenance. It doesn't require any user interaction. So why not take advantage of it if you can? So it's just down to good design. So just to make the point that this shouldn't cause overheating in the summer with our south-facing windows. Same model. It's now 7 o'clock in the morning. It's a day in August, and as we go through the day, you can see that that overhang's doing a pretty good job keeping the sun out, as you would hope. So it's nothing very clever, but it's good practice design. Now, in dwellings, when we talk about thermal mass, it's usually in the context of summertime and preventing overheating. And it's very effective at doing that. It soaks up excess heat gains inside the building, and in so doing, it stabilizes the internal temperature. It stops it becoming too high. You do, of course, need to get rid of that heat that's built up in the fabric, and we do that at night using the cool nighttime air to draw the heat back out of your walls and your floors, cool them down so that the next day they're once again ready to provide a beneficial radiant cooling effect to the occupants. So it's a sort of 24-hour heating and cooling cycle. So thermal mass is really good at that, but it is important that you ventilate the building properly to get rid of that accumulated heat. So you need quite large air change rates to do that. So perhaps we need to give more thought to summertime ventilation than perhaps we currently do, particularly in dwellings. So just to show you where you might find the thermal mass in a typical home, if you've got a concrete upper floor instead of a timber upper floor, that's an alternative option, you'll get a K value of between about 40 and 160. Now, I'm not going to get too technical. That's just a measure of thermal mass used in SAP and SBEM for Part L compliance purposes. To put it into context, a timber upper floor will have a K value of about 18, so it's quite a bit less. Lots of thermal mass in blockwork partitions and external masonry walls. So if you've got a cavity wall, the inner leaf of blockwork will give you up to 190 kilojoules per metre squared. That's using dense aggregate concrete blocks. And even if you've got dry lining, that will reduce the thermal mass, but even if you've got dry lining, it'll only reduce the K value by about 20% compared to a wet plaster finish, which is sort of the ultimate solution really in terms of thermal mass. It conducts the heat freely to the blockwork behind, so that's what you really want. Also acts as a really good, robust air barrier. And importantly, it's an air barrier you can actually see, so over the life of the building, if that becomes damaged, it's very easy to repair. And lots of thermal mass in concrete ground floors, which is a pretty standard feature in homes. And a tiled finish is fantastic. A little bit of mass in those, but like the wet plaster, it will conduct heat to and from the screed and the slab very effectively. Again, by way of comparison, timber frame house, the external walls, even with a brick outer leaf, will only have a K value of about 9 kilojoules. That's provided by the plasterboard on the internal finish, so considerably lower than a masonry wall. Okay, very briefly, I've only got a few minutes left. We like the White Collar Factory. Here's another photo of it. Let's a quick look at how we use thermal mass in commercial buildings or larger buildings, and generally it's used to provide cooling rather than passive heating, which I was just talking about. So why do we use exposed concrete soffits? Well, we lose about 60% of our body heat by radiation, and in order to be able to do that effectively, we need to be able to physically see other surfaces around us which are cooler than we are, because of course heat travels from hot to cold. Now the soffit is ideally placed for that. Firstly, it's very close by, wherever you are in the building, and distance is important. The closer those surfaces, the better. It has a very large surface area. That's very beneficial too. It doesn't tend to get covered up like internal walls and partitions do. And if it's made from a heavyweight material like concrete, it can store an awful lot of heat. And what that means is we can continue radiating heat to the soffit throughout the day, and it will hold on to that heat. And importantly, the soffit temperature will not increase by more than a couple of degrees, maybe 3 degrees. So even later in the day, when it's absorbed a lot of heat, it's still cooler than we are, and we can still radiate heat to it, so it's still providing that beneficial radiant cooling effect. So that's why we use concrete soffits. If it's a lightweight floor, it's going to warm up really quickly, and the effect doesn't last very long. Now there's lots of different systems for using exposed concrete soffits. They range from really simple systems to more complex hybrid systems where we've got a combination of passive and active cooling. For example, with the plastic pipework, which we heard about just now, embedded in the soffit, they give you higher cooling outputs and a greater level of control. But all of these systems have their own merits, and as I say, if you want to know more about them, do have a look at the publication we have on the Concrete Centre stand, which is just over there. And there's lots of case studies in there as well. Really briefly, a couple of examples. This is the simplest kind of system you can have. Naturally ventilated building. This is the Cambridge Federation of Women's Institutes headquarters. South facing, very well shaded with overhangs. And they've used precast concrete planks to form this building. And they use cross ventilation to cool it at night so you can get lots of air through. And they've got dedicated ventilation openings, and you can see one there in the back wall. Provides a very modest cooling output, but it's fine for that kind of environment. It's not too many people, not too much equipment, and it won't overheat. It shouldn't overheat. And at the other end of the scale, we've got the kind of system we've just been hearing about at the White Collar Factory, where we've got embedded pipework linked sometimes to a borehole, bringing up water at about 13 degrees. There's a lot of that in London. That's an ideal temperature for this system. So that goes to the pipework, and it creates a soffit temperature generally of around 20 degrees, and that in turn will ensure that the environment in the building doesn't go above about 25, 26 degrees. And you can also link it to a heat pump to boost the temperature to provide radiant heating during the heating season. So it's a sort of a year-round system. Another example of where it's been used is the Manchester Metropolitan University. And that uses the system I just showed you, which is lattice girder, precast lattice girder floors. And those are made at a precast factory. And as an example of one in production with all of the plastic pipework tie wrapped to the reinforcing, so the concrete is going to be poured on top of that onto a steel bed, which gives a really good quality surface finish. And there's one of the units at the Manchester University Business School being craned into position. These are about 12 metres long, 475 millimetres deep, so they're quite deep, but they've got void formers made from polystyrene to reduce the amount of in situ concrete that goes on top of these units. So it's a combination of in situ and precast. And that's the finished result, really high quality finish. And they actually used a combination of 75% white cement and 25% ordinary Portland cement to produce the precast units. So it gives a really light finish. No need to paint that, and really good from a daylighting perspective as well. Cuts down on artificial lighting, which is also important. And I think I'm probably out of time. So those are those two publications that I recommend to you.